We now switch our attention to the sequential circuits. What we have dealt with was the combinational logic modules, and those involved the basic gates, the modules like multiplexers, demultiplexers, decoders, adders, and comparators. All of these, we say they have no memory. They are said to be memoryless. But now when we shift our attention to the sequential circuits, we talk about the building block that allows us to have memory, which is a flip-flop. And the flip-flop becomes the basic building block of all synchronous sequential logic systems. It is considered to be a one-bit memory with two stable states, and therefore it is called a bistable element. In turn, the bistable element belongs to a class of electronic circuits referred to as multivibrators, and we are going to meet with a number of flip-flops. The most basic one is called SR flip-flop, and then an bit advanced to a JK, D, and T flip-flop. But we should also notice that these flip-flops can be able to perform the same function, whether it is the most simplest or the more advanced ones. They are able to perform similar functions despite their advancement. So we start the discussion of the memory of sequential circuits with the latch, and we say that the latch is a sequential circuit that has memory, but you cannot change its state from one state to another. The use of the memory is normally founded when you can store some data and then later delete that data and come up with some new data and store it at that location. But with the latch, the only thing you can do is that it has memory, but you can never store anything there. So that is the basic building block. But once we have understood the gate level implementation of that one-bit memory and its operation, we will see how we can modify it so that we can store memory and delete what was there previously and store new information. So that is the latch as an introduction. So consider this circuit that looks like it has feedback. This is a normal NAND gate, but of course it has one input, it has some input and the output. But what we are seeing is that the input of one NAND gate is being fed as the input to the other gate, and the output of this other gate called G2 is fed in as the input to the gate 1. And therefore what we see in this circuit is that this feeding of the output of one gate to another is what we refer to as the feedback. And for this reason, it is no longer classified as combinational but sequential. So the NAND gates G1 and G2 have the inputs shortened so as to serve as NOT gates or logic inverters. We met that concept earlier, where when you invert a NAND gate, you're going to have 1 and 1, and we know that when A, B, and output NAND is filled in a truth table, if you have 0, 0, we say the NAND displays a 1. And when we have 1, 1, we say that a NAND. So the shorting allows us to achieve an inverter. So we are able to consider the G1 as a NOT gate and the G2 as a NOT gate. So what we get from this gate comes here as the input, and therefore if it was a 1, this becomes a 0. And since we are getting this 1 from this, then this 0 comes in here as input and comes out as 1, and the 1 comes here as 1, this comes as 0. And for that reason, we say that the two inputs will always be considered to be opposite of each other. So what we observe with these two inputs is that they are always going to be, the two outputs are always going to be complementary, and hence we identify them as Q and Q bar. We say this can be expressed as Q bar, this is Q. So they are always complementary of each other. And the circuit has two states that we can denote as Q and Q bar. In the set state, also referred to as one state, the Q is 1. So we say our latch will be set when Q is 1, and at that point Q bar is 0. And it is in the set state when Q is 0 and Q bar is 1. So how are we able to get the set state? That is Q is 1. We're able to get Q is 1 when the Q bar is 0, which is this output of Q bar is fed to the gate 1, and when the gate 1 is fed input 0, then the output of that gate becomes logic 1. And once we get the logic 1, this logic 1 is fed as the input of G2, and what we get at the output of G2 is this 0 again. So that is how we are able to maintain the locked state of set state for the latch. On the other hand, in the reset state, the outputs are vice versa. That is, output of Q is 0 and the Q bar is 1. And what we have said about the latch is that if it is in set state, it will not change. It will remain in that state because the feedback we are getting will always be the same. This state is referred to as memory, and that is what consists of the latch being said to store 1 bit of digital information. But we have said that that locked state is what limits the latch from remaining or from changing to another state. We say that it is locked, it cannot change from one state to another, and for that reason it is not useful. It is just a memory that you can never store anything. But that foundation allows us to talk about the flip-flop, which is called SR, and SR simply means set reset flip-flop. So we are saying that this SR flip-flop is simply called SR because it can have 2 states, that is offset and reset, and hence the name SR flip-flop. So how do we get this unclocked, first and foremost, SR flip-flop? We'll talk about the clocking because it is the clocking that allows us to change the state of our flip-flop. So we are just modifying, this is what we consider to be the latch, but now we are saying that if we input, instead of knotting or shorting our gate 1 and gate 2, remember it was shorted and therefore this was getting us 1 input. Instead of now shorting the inputs of our 2 gates G1 and G2, if we feed that gate with an inverted version of S input and R input, then we are going to get that flip-flop that will have the characteristic of set and reset states. And what we will simply do is to observe what happens when we have S at 0 and R at 0, S at 0 and R at 1, 1, 0 and 1, 1. Just the way we look at the 4 possible combinations of any input. So if we draw a truth table of S and R or SR flip-flop, and you observe the output of this flip-flop, the way it's drawn here, we will just observe what are the outputs when our input variables are changing, as we normally observe for any 2 variable input. We ask ourselves, for instance, if we set S to be 0 and R to be 0, what will be the output? And assume the output was 0 here, and therefore if the Q was 0, definitely the Q bar was 1. So we will consider this to be a 1 coming here, and what is coming out of this is a NAND gate that is shorted, which is acting as a NOT gate. Therefore this will come out here as a 1. When you give a 1, 1 to an NAND gate, we know that we can always draw the NAND gate truth table here. We normally see that the output is 1, 0, 0, 0. So when we have 1, 1, we can see that the output here is 0, and therefore since our output was 0, after the application of a 0 in S, the output has not changed. So if the initial state was 0, it remains as 0. Let's see, the other possibility is if output was 1 and therefore the Q bar was 0, we would then have this 0 come in here, and still our S is still at 0, so our output of G3 is a 1. What we will be feeding to our G1 is now 1, 0. And we know 1, 0 is, I observe a correction here for the sake of clarity. I made that mistake, which I correct now. I observe that AND gate, probably we can just include AND gate here. This will be 0, 0, 0, 1. And therefore, when talk about NAND gate, this is opposite of NAND, which is 1, 1, 0. So that is a mistake I had done. So we are again saying that this is 0, comes in here as 0, and this is 0, comes out here as 1. And therefore, when you input 1, 0 to the NAND gate, the output, when you have 1, 0, remains 1. So this output will still be 1. And therefore, if the previous output was 1, the next output will still be 1. And how do we classify that? We normally say that when S is 0 and R is 0, there is no change. We normally say that output, which I would have wanted to put it there, is no change in output. So let's observe if, on the other hand, our inputs are 0, 1. So if S is 0 and R is 1, we indicate 1 here, and this 1 will come out here as 0. And since the previous state, we can start with the previous state of 1. Since the previous state is 1, comes in as 1 here, then the output of this gate 2 is going to be a 1. And this 1 will now come here as a 1. And when you feed G1 with 1, 1, the output of a 1, 1 is a 0. So we observe that if the previous output was a 1, it will become a 0. And let's observe if the previous state was a 0, what will happen? So we are saying this was previously a 0, and therefore this was a 1. We are feeding R with a 1, therefore the output of G4 becomes a 0. So this 0 you would feed it here becomes there as 0, because that was the previous state. So the output of G2 with 2 inputs 0, 0, the output becomes 1. So the 1 comes here, and you remember that this is an inverter, becomes 1. So again, 1, 1 will still give us a 0. For that reason, what we say, if it was 0, it will still become a 0. Therefore, we are saying that when we have set S to be 0 and R to be 1, the output will be a 0. So we can now consider when S is 0 and R is 1. What happens? This is a 1 and R is a 0. And we can start with the previous state being a 0. What we say is that this 0 will come here, and our output of G4 will be a 1. So therefore the output of G2 becomes a 1, and this 1 comes here. And since this is a 1, this is a 0. Therefore, when you get inputs of G1 as 0, 1, definitely this 0, 1 will give us a 1 out. So if it was previously a 0, it will become a 1. Let's see if this output was previously a 1, what will happen? So this was a 1. So what we get here in this G2 is a 1, and our R is still a 0. So 0 comes out of G4 as a 1. We feed G2 with 1, 1. We know when we feed G2 with 1, 1, we are getting a 0. So we get a 0 here. So 0 is fed right there, and therefore our S is 1, comes out of G3 as 0. So we're giving it a 0, 0. And therefore, when we give an AND gate a 0, 0, again the output is going to be a 1, because we are here. And therefore a 1, 1. So when it was previously a 1 and we have set our inputs as 1, 0, again the output will still be a 1. Therefore, we say that no matter what the previous state was, the output will be a 1. We will not look at this one because there is some ambiguity here, and therefore we normally say that the S and R should not be set as 1, 1. And therefore, we have come up with the truth table of SR flip-flop that says that if you have S as 0, R as 0, the output there will be no change to the output. If it was 1, it will remain 1. If it was 0, it will remain 0. If you give the input S as 0, R as 1, then no matter what the previous state was, the next state will be a 0. And if you set your S to be 1 and R to be 0, no matter what the previous state was, the next state will be a a 1, and we don't work with the 1 inputs, and this is normally referred to as an ambiguous state, and that's what we have developed can clearly be seen in this table right here. So this is what we have developed. We have said that when S is 0, R is 0, there is no change in the output. When S is 0, R is 1, the next state will be a 0, 1, 0, 1, and with 1, 1, this is called ambiguous, and therefore we never use that state. That for us is an unclocked flip-flop.